But lectures are online.
It is really quiet, by the way, your lecture.
It was really quiet.
Well, I had my volume up and, yeah.
Well,
Any noise that I had in the house, it covered over your.
What assistant you to
I'll try and drown out outside noise and talk a little quieter. How's that?
Good.
But yeah, you're probably going to want to watch these with headphones. I would just listen to it.
Well, I was just in my room. And any noise in the entry, I have a hard time hearing it.
Sorry. Don't know what else to do.
Is it dull?
Because if I move it closer, yeah.
It cuts out the board, yeah.
Well, no, if I move it, yeah, it cuts out the board, and so I'd either have to have someone operating the camera, going back and forth. But yeah, if we're closer to pick up my voice better. Like geometry lectures, you can hear me way better, but that's because I only have one word to use.
Yeah.
Anyways, so if it stays that bad, then I can force myself to one board and get set up so I just use this board.
It's pretty loud.
Might need a laptop.
It'd be cool to get a mic.
That's what I'm saying, I use headphones. Because that might get it through a lot better. Anyways, so last class we ended talking about the field axioms. So let's review those real quick and then we'll go over the two proofs that we did and then we'll continue from there. So, the field axioms, remember, we're trying to give meaning to this set R. That's what we're trying to do. So we've got the set R, and we've got two operations, plus and multiply. What do we know about plus and multiply? We know that if you take two elements out of R and you add them together, it gives you another element in R. We know that.
Right.
Same thing with the multiply. So we know that, and then we have these axioms that we also know. Okay? It's all the information that we have so far. So we know a real number plus a real number is a real number times a real number is a real number, and then we know that these axioms are set aside. So we know x plus y, same thing as y plus x. X plus y plus z is the same thing as y plus z, then add the x. We know that there is in the real numbers some zero element, such that any real number plus that zero element just gives you back the real number. Call that the additive identity. We know that for every real number, there is at least one other number, such that when you add the two together, you get a 0. If x is negative 4, then y is 4. So we know there's at least one. Does that make sense?
Yeah.
And then we have a repeat of the same two properties again, except for this time multiplication. We have that there is some number in the real numbers, such that any real number times that number gives you back a different real number. I said that terribly. But you understand what that means, right? Multiplicative identity. And then we know that for any real number you pick, there's at least one other real number. For all real numbers, there exists a real number, such that the product of the two equals 1. You give me negative 4, I give you negative 1/4. Any real number you give me, I can find another real number such that the product is 1. Good? And then this just tells us how to combine our multiplication and addition operation. And then this is just making sure that we're not talking about set with just one element in it. Okay? So that's what the field axioms are, and then we did these two proofs last time. And the lectures are online. I'll typically get the lectures up the first work day after we have class. So this lecture probably won't be up until Monday afternoon, is when I would guess. But that's typically how quick the lectures will go up. So we proved this one last time. There is only one 0 element in R. So remember, this only guaranteed us that there was at least one. Then we prove that there is one and only one. Does that make sense?
Yeah.
So we didn't need to assume that there was one and only one. This was enough information to capture it. That's what we try and do with these axioms. We try to figure out what's the minimum amount of information we need to prove all the math that we want to prove. So we didn't need to say that there is one and only one zero element. Sorry, this line. One and only one zero element. We just said there is at least one, and it turns out that the other axioms require that there's one and only one. Does that make sense? The difference between this and what this gives us?
Yeah.
Okay. This one, we prove that a real number times 0 is 0. Or 0 times a real number is 0. Good? Alright, so that's where we ended off last time. So, continuing with these proofs. By the way, the author doesn't prove any of these. So, you can't go back to your book to reference these proofs. Did you all get the book?
Mm-hmm.
You got it?
I haven't looked.
You haven't looked? You haven't looked at the book? And we're on our second class?
Yeah.
That's not good. Alright. So, the author doesn't prove most of these. Oh, he does actually in the appendix. Do you guys understand what an appendix is?
No.
Is
So-
that where they put all the formulas and?
Not necessarily, but that is common. So, a lot of the times, I'll talk only in the context of math textbooks. A lot of times in math textbooks, the author just says, this is true, and continues on his merry way. And he puts the proof of it in an appendix.
Oh.
So why does he do that? So he doesn't fill his chapter with stuff that you probably don't care about. But if you do care about it, there's a place to go get the material. And then it's also, sometimes math authors will put in there really quick reviews of other material that the textbook presupposes. So, for example, the textbook that we're using, it also has a review of linear algebra. Now, we'll never get to linear algebra material in this course. We'll stop before then. That's for multivariable calculus, but it's in there. And there's an example of that where it gives a quick review. So anyways, you can find the material in the appendix, not in the actual chapter. Okay? And your homework problems that I assigned you, your test problems, they're in the appendix. So I told you the page number to go look on. And that is due Tuesday. So as far as our syllabus goes, last class and this class together we're going to call week 1, and then from there on out we're following the syllabus. Make sense? Alright. So let's move on now to our next proof. So our next proof, we're going to prove that if A times B is 0, then either A is 0 or B is 0. Now they could both be 0, that's a logical or, right? But at least one of the two is 0. So here's it in terms of our logic notation that we used last time. We're saying that A times B equal to 0 implies A equals 0 or B equals 0.
Why did we prove that? I thought that's already proved.
How is it proved?
Because we figured out that 0 times any number is 0.
Yeah, we know that if one of those numbers are 0, then this is 0. Now we're proving if this is 0, then one of those numbers are 0.
Yeah, that's what we proved, but it seems like it proved.
Maybe there's two other numbers out there. Maybe 4 times 79 together gives you 0. You see what we're saying? So maybe there's two magical numbers out there that when you multiply together, you get 0 without actually using 0. We're going to prove that's not the case. So does it make sense what we're trying to prove?
Yeah.
And like I said, it's really hard when you prove these things to figure out where to start because you want to assume so much knowledge that you already have about math. So let's go over it. So first off, so we're trying to show that if A times B equals 0, then this is true. How do you do proofs? You assume, so all theorems are in the form of if A, then B. Right?
Yeah.
So if I want to prove that A implies B, how do I do it? I assume
A is something.
A equals true, and then I prove then B equals true.
Okay.
Okay? That's how you do proofs in general. So if I want to show that if this is true, then this is true, I assume this is true, and I continue from there to show this is true. Okay? So my proof makes this underlying assumption that A times B equals 0. And I didn't write that. Maybe I should have put that step in there. 0. That's step 0 instead of step 1, like where it should be step 1. Let A be in R such that A times B equals 0. Maybe I should have put that step
That's
there.
not observing what, that's not assuming anything, is it?
Yeah, I'm saying let A and B be real numbers such that their product equals 0.
Well,
That's what the condition wants.
Yeah.
It wants two real numbers such that their product equals 0. So what I'm saying is sometimes a lot of proofs leave out this step and they say you're going to instantly assume this information because that was the if part of the theorem.
Right.
Does that make sense?
Yeah.
Am I losing you?
No.
You're with me? Alright. So I made the assumption that we have two real numbers, A and B, such that A times B equals 0. I made that assumption when I did this proof. Because that was the if part of this.
Right. So
Okay.
in your proofs, you just put the if part as your first step.
As when you first get into proofs, it's good to be very explicit, write everything out. And as time goes on, you'll develop your own predilections and patterns and whatever. Or your own style of proving. I have my own style of proving. Like I like to number things on the side. Most people when they prove don't do that. Alright. So, let's begin. So, we're trying to show that if this is true, then A equals 0 or B equals 0. Okay? Now, if A equals 0, then the proof is already done, right?
Yeah.
So I'm going to assume A doesn't equal 0. So I need to show that this is true when A equals 0 and when A doesn't equal 0, right? That's handling all cases.
So if A is not 0, then we want to prove false, right?
No, so sometimes, let's say I've got a set of things and I want to make a proof about everything in set A. And I don't know how to handle everything in set A at once. So sometimes I split set A into two cases, case 1 and case 2. And then I prove this case separately and this case separately, and that handles all cases.
Prove it true.
Yeah, I prove that the theorem holds for all these cases and for all these cases instead of proving it for everything all at once.
But you want.
So I'm going to prove it for all the cases where A is equal to 0, and I'm going to prove for all the cases where A is not equal to 0.
Well, how do you prove that when A is not 0, when our whole idea is to try to get A or a number times 0 equals 0?
So if you pick any two real numbers,
Yeah.
one of the two cases, you pick A to be 0 or you pick A not to be 0. I'm going to show that the theorem's true either way.
How? Because you need the 0.
I'll show you how.
Okay.
But do you understand what I'm saying?
Yeah.
So handle the top case. If A equals 0, then we're done. If A equals 0, then the proof is done. If A is 0, then A is 0, which is what we're trying to show. We're trying to show A or B is 0. We're trying to show if this is true, then this is true. Well, if A is 0, then this is already true. If A is 0, A or B is 0.
So now you're trying to.
So we're done. Now I'm going to say, now let's handle this case where A isn't 0.
Okay.
So then assume A isn't 0.
Okay.
Now we still know,
The easy there is 1, right?
so then assume A isn't 0.
Never exists.
Observe that, I missed a very important line. Sorry. For all x in R, where x is not equal to 0. So let's make sure we understand step 8 again. For any real number you pick, I can find another real number such that their product is 1, unless you pick 0. Right? So, the only way that I can say this about A is if A is not 0. So, assume A is not 0, then there must be some y in the real number such that A times that y equals 1, using this.
Okay, what does y represent in this context?
If A is 1/4, y is 4.
Okay, so it's the supplementary number, or it's the other number.
What we're going to end up calling it is the multiplicative inverse.
Okay.
If A is 5/4, y is 4/5. Does that make sense?
Yeah.
But we don't know what it is. So assume A is not 0. So
My whole point in saying y is y. Y is not just some random number. Y is directly dependent on what our x is.
So let's make sure that we understand this. I'm saying that for any real number you pick, as long as it's not 0,
There's a y.
there is at least one y in the real numbers, such that their product equals 1.
Right.
So here you have some random A that's not 0. You have some random real number that's not 0. I am guaranteed
There's a one.
that there is at least one y inside the real numbers such that their product equals 1.
Okay, I'm 100% with you.
Okay, good. These are great questions because getting used to how we use these for all there exists type logic, it takes steps. And we're doing what I take like 4 classes to do in discrete math, all in 2 classes, so it's a lot. Alright. Oh, we're up here.
4.
So we know that a is not equal to 0. So that means that there must be some y in the real numbers such that the product of a with y equals 1.
Yeah.
Right? Okay. So we know that a equals 0. That's right here, or we could say that's step 0. Let a and b be real numbers such that a equals 0. That's a comment to the top line, that's not apparent anymore. Anyways, so we know that a times b equals 0, right? And we know that we can multiply both sides of our equation by the same thing. So from here to here, I multiply both sides by y.
Okay.
Good? From here to here, I use the associative and commutative property on this to reorder, so it's a y times b. And then I use the fact, use our proof right here, that 0 times y is 0.
Okay, now one sec. I was always told in my mathematics that it does not work in mathematics to times one side of your equation by something and the other side of your equation by something if one side of your equation is 0.
If you have a true equation, you can multiply both sides of your equation by any number, and you still have a true equation. So, if I have, you just might lose information in the process if you multiply by 0. So if I have 5x equals 72 plus 6, there's information about what x equals in there, right? But it's perfectly valid for me to multiply both sides by 0, and then I get 0 equals 0.
Okay.
So the equation is still true. It's just you lost information in the process. So even if that y was 0, which we know it's not from our own experience, but even if that y was 0, multiplying both sides by 0 still keeps the equation true.
Multiplying both sides by the same number and one side is 0 doesn't seem intuitively right.
If I have an equation and one side is 0, and it's a true equation, the other side is 0.
Okay, well, it's like 6x plus 7 equals 0.
So if I have 6x plus 7 equals 0, I can then multiply both sides of the equation by 0 and still have a true
By
equation.
4. By 4. Multiply each side of the equation by 4.
Then it still works.
Oh yeah, it does. I see why.
Okay.
Okay, I'm sorry.
Now that's fine. You're getting back into math. Alright. So we can multiply both sides of the equation by the same thing, and it doesn't change the equation. So here I multiply both sides by y. Then I rewrite my equation. On the left-hand side, use commutative and associative properties to reorder it and regroup it. And then on the right-hand side, I'm saying 0 times y is 0. We know that from this. We know that any real number times 0 is 0. We prove that. So that means y times 0 is 0. So you good with going from this equation to this equation?
Yeah.
Alright, now let's take it one more. What is a times y?
Gonna be 1.
Yeah, that's 1. That's how we chose our y. We chose our y such that a times y equals 1. That was our specific choice of y. So a times y is 1. So now we know 1b equals 0, or in other words, we know b equals 0.
Do we have proof that 1 is?
That's an assumption, not proof. Right?
My question is, you reorder things, but how do you know when you should reorder things?
You have to think backwards.
Because that's what I struggle the most with proofs, is reordering stuff and using properties to do that.
It's like equations are easy, you just get simpler. With proofs you get like...
Okay. Let me show you some general techniques for proving with a side proof real quick. So, you don't know divisible. I was going to show that an even plus an even is an even.
Wait, let's finish this proof real quick.
Yeah, let's finish the proof, then I'll go over how you do this. Yeah, okay. Alright, so you good with here?
Yeah.
B equals 0. So we just barely showed, so there were two cases. Either A equals 0 or it doesn't. Right?
Mm-hmm.
If A equals 0, then we're done. A equals 0. That's what we're trying to prove. We're trying to prove A or B equals 0. If A doesn't equal 0, then B equals 0. Therefore, if A doesn't equal 0, then B equals 0. So we handle all the cases. Either A equals 0 or it doesn't. If A doesn't equal 0, or if A equals 0, then A or B equals 0 is true. Good. If A doesn't equal 0, then B equals 0. And therefore the statement A or B equals 0 is true.
That was actually so cool.
So in either case, the statement's true.
That's cool.
And you see how we split it up into two cases? We split up into all the ABs where A is 0. And we split up into all the ABs where A is not 0. And we proved it for each of those cases. Good?
Mm-hmm.
Wonderful. Alright, so side proof. To help give you some general ideas for proving. And I want to pick like a real easy proof with a couple definitions in it.
By the way, when we're proving in our homework, we have to say, like, right there, we use the commutative property, the two-column proof.
Let's address this real quick. I personally hate the column proofs. Because it's this idea that you need to break each step up to what we have a rule for, rather than each step up to what you feel like is a logical step to take. So just explain it. Like, if you're comfortable saying, and then this equation gives you this equation, using the associative and commutative property for the left-hand side, and using proof
So write
2.
that out.
Yeah, you
So
explain
like,
it.
your proof right here is not.
No, my proof is a sketch because I'm explaining and showing at the same time.
But on our homework, we're gonna be writing like.
You're going to be writing like crazy until, if you feel like I've already written this a lot, or here's a common way to know that your proofs are good enough. Think about your fellow classmates. If they can follow your logic step by step, knowing exactly what you're doing, then you're typically good. That's a good way to think about how much explaining should I do. And so early in the year, you should be doing a lot more explaining about proofs than you would later in the year. If you went back and did this proof at the end of the year and it looked exactly like this, I'd be perfectly fine with that, with one reference to make sure that when you do this, you actually reference this proof. Other than that, I would have been fine with it.
Okay.
Does that make sense?
Yeah.
So write for the people that you're with. Now, these proofs, we're just using these axioms over and over again. So you don't get a good general idea of how you do proofs, common techniques for doing proofs, which unfortunately isn't something that we really get covered in this class. And seniors can't take discrete math. I really wish it could have been in this class and discrete math. Because then you could get learning how to do proofs while learning awesome proofs at the same time. So let me just give you one example real quick of what's common to do. Divides is an operation on integers. And the way that we write it is A divides B. And what does that mean? When I say that A divides B, that means that there exists some integer C such that A times C equals B. That's what it means. So I'll give you a quick intuition. I say, does 2 divide 8?
Yeah.
Yeah. How do you know 2 divides 8? Because there is some integer, namely 4, such that 2 times 4 equals 8.
Right.
Does 2 divide 9?
No.
No. There is no integer, C, such that 2 times something equals 9. You can't take 2 times an integer and get 9. Now, over here we're just talking about integers, over here we're talking about real numbers, so I don't want to confuse them. In discrete math, we start with simpler sets.
So
to
when
get
I
you
say
full
2 divided by 4 with a calculator, that's an approximation.
No. This is divides, not divided by. This is a statement. This is an operation. This takes out 2 numbers and gives you a number. This does not take out 2 numbers and gives you a number. This is a statement that's either true or false. A divides B. 2 divides 8 is either true or false. 2 divides 9 is either true or false. 2 divided by 8 is a number. 2 divided by 9 is a number. So this has nothing to do with division.
Okay.
Does that make sense? So there's divides, and then we have our definition of even in class. Even. And A is even is logically equivalent to 2 divides A. So if 2 divides A, or A is divisible by 2, then A is even. Okay? So do you feel like you understand these two definitions?
Yeah.
Sorry, it's kind of a lot of work to set up just a basic proof, but I know an easier way to do it. So now let's do a basic proof. Proof uneven plus uneven is even might be how I worded this. Step 1. Any theorem that you're trying to prove can be broken up into an if-then statement. Okay?
If you add two evens, then you get an even.
Right. So step 1 when you're trying to prove something, break it up into an if-then statement. So we want to break it up into if, and it's also useful to add variables to talk about things so you can reference them in your proof. So I might rewrite this as if x and y are even, then x plus y is even. Does that make sense?
Yeah.
Yeah.
So here, you might be a little bit confused about where to begin. But if you re-break it up into an if-then statement, you start with the if, and you conclude the then. So the first line of my proof then would be whatever the if part is. I would say let whatever comes after if. Let x and y be even. And we assume that we're talking about only integers. Okay? And then I go to my last line. I don't remember this maybe yet. But my end of my proof is, therefore, x plus y is even. Okay? So this is where I'm starting, this is where I'm trying to get. So this is common strategy that you would use over and over again. You say, where am I starting, where am I trying to get? And then the next step you do is what we call unraveling definitions. You just write out what exactly does a statement mean using its definitions, and what exactly does a statement mean using its definitions. This one you work bottom up, this one you work top down. And then there's going to be some point where there's just a gap in the middle, and then you got to figure out how to connect the gap. Okay? So let's start unraveling these definitions. Then we'll unravel these definitions, and then we'll figure out the middle part. So 2. So if x and y are even, what does that mean?
They're divisible by 2.
Yeah, then 2 divides x and 2 divides y. Notice we're not done though, because we know what that means. What does it mean for 2 to divide x?
There's
That's
an
equal.
integer
No, there's an
times 2
integer.
that equals.
Right, use this definition now. So 3, then there exists, I'll call them A, B, such that x equals to A and y equals to B. See how I'm choosing that definition?
There is A, B.
So since 2 divides x, then there must be some integer, I'm calling it A, such that 2 times A equals x. And since 2 divides y, then there must be some integer, I'm calling it B, such that 2 times B equals y. With me?
Mm-hmm.
Now unravel this definition. Now notice we don't really know what to do from here. We can't unravel definitions anymore. And that's kind of like the simplest information we can, the simplest way we can write it. We've used all our definitions. So now go to the bottom and start using your definitions and work your way out. Once again, what does it mean for x plus y to be even?
That x plus y can be divided by 2.
Then 2 divides x plus y, right?
Good.
What does it mean for 2 to divide x plus y?
X times x plus y.
Then there's some integer, c, such that 2 times c equals x plus y. Maybe I should have written. Then there exists c such that 2 times c equals x plus y. right? Now, one more logical step that I might want to take is, down here I'm talking about x plus y, up here I have an x and a y. Let's talk about x plus y. Okay? So this is unraveling definitions. Now we gotta figure out how to fill in the gap. We gotta figure out how to go from here to here.
Could you do x plus y equals 2a plus 2b? Or do we not know that?
No, we do know that. We know what x is. We know what y is. So that's exactly the next step that we probably take. We write 4, therefore x plus y is equal to 2a plus 2b is equal to 2 times a plus b. Then I might say 5, let c equal a plus b. 6, 7, 8, we're done. Yeah, that's fine.
A plus b, 2c. Oh, because x plus y is 2a plus
You see it?
2 divides it. Yeah, because of that, we have that one. So 2 times an integer is equals.
So this is a common way that you go about proving something. You take your statement, break it up into the condition and the conclusion. The condition becomes the first line of your proof. The conclusion becomes the last line of your proof. The vast majority of the time, whatever you're proving is using definitions. So you unravel your definitions, and then to connect these two lines, there's no surefire way to do it. That's the thing that the only way to figure out how to do it is to get comfortable proving.
Is your therefore always your connection? Because you always have therefore in the book.
It's just common vernacular. When you use then or therefore is kind of just a preference. I mean, I could have used then, all the way and never said therefore. I try to reserve the word therefore for major leaps that you make. So let x and y be even, therefore x plus y is 2a plus b, therefore x plus y is even. So that's the way I like to use the word therefore, but once again, it's just preference. Okay, so that's the general way that you go about doing proofs. Here we don't have definitions. Here, that's another reason that these proofs kind of feel unguided, and you just kind of got to figure it out. You can see where you start and where you're trying to get. So the case where a equals 0, not much we can do there, but we could have said, handling the second case, assume a is not equal to 0 is what we're going to start with. And we knew that we wanted, therefore, b is equal to 0. Right? But figuring out how to fill these in isn't as straightforward as a proof like this. These are more difficult proofs, even though they feel like they're using simpler things. It's because you're not using definitions directly. Right now you're referencing axioms. Like there's no way to start here and know, okay, now the axiom that I need to use is,
Okay, now that we've proved that a times 0 equals 0, or sorry, now that we've proved, that a times 0 equals 0, we can use that in proofs now, right?
yes,
Okay.
absolutely. Do never, 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 never reprove something. Once you prove it, reference it.
So we're not only using field axioms in our proofs.
Right, so in this proof, I have this information to work with and the field axioms. Now in this proof, I have these proofs to work with and the field axioms. And so as you go through this class, you're going to add on and add on and add on. That's one of the crucial reasons that you cannot miss material in class. Because chances are, as you build up, this is going to reference what we just used. This is going to reference what we just used. And so as you go throughout this class, if you miss a class in the next class, chances are we're going to be doing proofs based off the material from the previous class.
Right.
And it keeps building that way, so it's a tough thing to miss, let alone its complex material in and of itself. Okay, so that was a discrete math style proof. Would have been a fun class, huh?
Yeah. You've proved this before, James?
Yeah, they prove all sorts of things. So the regained proofs in class is that an even plus an even is an even, an odd plus an odd is an even times an even is an even, an odd times an odd is an odd. And we'll probably do a couple of those proofs because we're going to need the fact that a squared is even implies a is even, and a squared is odd implies a is odd. But we'll get there. Alright, so that was that proof. Now let's move on to this proof. So let's see what we're trying to prove next. So looking at this line right here, we knew that for any real number you pick, I can find another real number such that their sum equals 0, right?
Yeah.
What we're going to prove is that not only can I find a real number such that their sum is 0, but I can only find one. I can find one and only one. And this is going to enable us to define something called the additive inverse, which is how we're going to define negative numbers. So I'm going to want to say that negative a is a number such that a plus negative a equals 0. The only way that I can make that definition is if negative a only references one number. I can't have that referencing three numbers. So that's a little bit of the motive for why we want this. It helps us make this definition that we're going to use later. And so, make sure you understand the difference. This is saying, where is it? This is saying that for any number you pick, I can find a number so that their sum is 0. We're going to prove that for any number you pick, there is one and only one number that you can find such that their sum is 0. That make sense? Okay, so that's what we're going to prove. And this is kind of similar to there's only one 0 on it. Right? We're going to do a proof by contradiction, kind of like we did with 0. So, let's read the statement and make sure it makes sense. For all real numbers, we're going to call it A. Or for any real number A, there's another way you can read that. There exists, that exclamation point after the there exists sign means one and only one. So there exists one and only one, B, in R such that their sum is 0. So for any real number you pick, there is only one other real number such that their sum is 0. And I shouldn't have said one other because it could be A is 0 and B is 0. So let me say it one more time. For any real number you pick, there is one and only one real number such that their sum is 0. That make sense? Think you understand the statement? You understand how this is different than our axiom?
Yeah.
Yes.
Okay, so let's prove it. So assume by way of contradiction that there is some b prime such that a plus b prime
Is prime meaning a different number than b?
yeah, so that's very common notation. If you just want to use the same variable so you know the two are associated, but you also want to make it different, you can do prime or subscripts on it. That makes sense?
Yeah.
So that's not a derivative symbol for those of you who have already taken calculus. That's not what we're talking about. We're talking about just a different number, some way associated with b. So assume by way of contradiction that there is some element b prime, some other element, we'll call it b prime, such that a plus b prime equals 0, and b and b prime are not the same thing. You with me?
Yeah. This is the same thing we did for we did it for x plus y.
Yeah.
We did it here.
Yeah, there we go.
We did when we were proving that there's only one 0. That's a common way to show that there's only one. Assume that there's more than one. Assume by way of contradiction that there's more than one. And show that that's impossible. Show that there being more than one is always impossible. Therefore, there's only one. And why can't there be 0 of them?
Why can't there be 0?
Yeah, we're saying,
Because
we're proving that there's not more than one, but why can...
Number 4 field axiom.
Right, number 4 says there's at least one. Now we're going to prove that there's not more than one.
Yeah. Your point in saying that is the same reason why you said you prove all cases. We already proved one case.
Yeah, one case wasn't proven, one case we get for free.
Right.
The case we get for free is that there's more than one. Or that there's at least one.
Yeah.
Not more than one. Because we're going to prove that there's not one. Okay. So, then, b prime. Now, big picture, what am I trying to do? I'm trying to show that B prime equals B,
Yeah.
right?
Trying to show that that's not possible.
So that's not possible. Assume by way of contradiction that there is some B prime such that A plus B prime equals 0 and B does not equal 0. So I'm going to use this information that A plus B prime equals 0 and show that leads to B equaling B prime.
Right. There you go. Yeah.
Does that make sense?
Yeah.
You with what I'm trying to do?
Yeah. If
Right.
B equals B prime, you know that there's only just one B.
And I know that I'm going to have to use this property somehow. Okay? Because that's what we're saying can't be true. There can't be some other number that has this property. Because if it has this property, then it's going to be B.
Right.
Alright. So everyone sees big picture what we're doing? Okay. So then B prime is equal to B prime plus 0 is equal to B prime plus, what's another way I can write 0?
A plus B prime.
Yeah.
But I don't want another B prime. I'm trying to get my B in here somehow.
A plus B.
A plus B. My whole goal is to somehow get B into this equation. Because I'm trying to get B prime equals B and I'm done. So that's how I did it. Okay, now how do I get just B over there?
Just
You
B.
do
Community.
the one where you can switch.
Or associated.
Yeah, so I'll rewrite this as A prime plus B.
A plus B prime
A plus B prime
plus B.
plus, thank you, jeez, plus B, right?
Mhm.
And then what's A plus B prime?
Zero.
A plus B
You
prime.
can probably write that.
0. 0 plus B, which equals B. Right?
Yeah. There you go. Wait, no, you just got rid of your B prime. You want to prove that B prime.
B prime equals
Okay.
B.
There you go.
Maybe write that as the last line. 3. Therefore, if that's not an obvious leap, B prime equals, I don't even know how to write it. B.
So how do you end?
Contradiction.
Okay, that's how you end the proof.
No, that's how you say. So, think about it like, you know, through programming. Think about it like a paragraph. When you start a paragraph, you do an indent. When you end a paragraph, you have a blank space between it. Here I'm saying I started a proof by contradiction. This says I finished my proof by contradiction. Now I can continue with the proof in general.
Okay.
But the contradiction is part of the proof. You see how this is closing this?
Okay, yeah. I see.
Okay. 4. Therefore,
If B equals.
therefore, no such B prime exists.
Because. Do I have to write that crap out? Do I have to say because?
No, because if it did exist, then
Right.
this and this and this. You end up in a loop again.
You know, they'd have to assume.
So assume by way of contradiction that a B prime exists. If that B prime exists with those properties, then we get a contradiction. Therefore, no such B prime exists. Or therefore, our assumption that B prime exists is false. And then you can write, therefore, what we were trying to prove is true. Good?
Yeah.
You like it? You ready to start doing some of these proofs yourself?
Yeah, I'm going to try one.
Well, you've got 4 that you get tried. Sorry. If I had time, I would have made up some more for you guys, but
You could do prime.
I'm saying maybe a couple more problems for you. I just assigned the problems that the author already had. So, question?
My question is, so when we're writing our proofs, blah blah blah, whatever. When we have a proof and we want to reference this proof, how do we do it? Do we just say proof number 3?
So the author has these proofs labeled in the book. Sorry. Oh, jeez. Outward. The author has, now he omits these proofs and puts them in the appendix, but he still has the statements in the book. And he labels the statements as proposition 1, proposition 2, proposition 3, etc. Or theorem 1, theorem 2, theorem 3. So you say by proposition 2, da 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 da. So these things actually have names.
So he doesn't prove them.
I just didn't name them.
He already assumes they're proved. Or he already
Yeah, so his textbook is meant to be more,
calculus.
not more calculus, but more malleable, I guess. It can apply to different contexts of students. For some people, going through these proofs is a waste of their time. They're like, we've done this. We've been there, we've done that. But for other people, it's important. So he puts it in his preliminaries, which is, these are things that you're expected to already know. In case you don't, check the appendix.
Okay. So we're still not even into the textbook.
Yeah, we haven't started chapter 1. We're still in the preliminaries. Because you guys aren't near as familiar with this material as the intended audience in the textbook. Does that make sense? Alright. Let's see. So now we have a little definition. Given A in R, let negative A in R be the unique number such that A plus negative A equals 0. In other words, we're defining our negative symbol.
I'm just going to say we've never done negatives.
Yeah, so now we have a definition of what that negative symbol means. That's what we're defining right now. What does that negative symbol mean? What is negative A? It's the additive inverse of A. It's the unique number such that when you add it to A, you get 0.
Do you mean unique by one and only one?
One and only one. That's exactly what I mean by unique. So if I want to talk about what's the additive inverse of negative 4, how would I denote that?
There's only one.
What's the additive inverse of negative 4?
4.
Negative 4. That's its additive inverse. Now it turns out that is 4, and we'll prove that. But that's what we're saying. For any number you have, we're defining this to be, that's not equal.
Oh,
We're defining the negative symbol.
You just attach this negative symbol on, then you got your
Right.
negatives.
So if I have some number x, then I'm guaranteed that x plus negative x is equal to 0. So if x is negative 7, then when I plus negative 7, I get 0. If x is 2, then when I plus negative 2, I get 0. We're defining what that negative symbol means. We don't prove that 2 plus negative 2 is 0. It's our definition of what negative 2 is. So now negative 2 has meaning. So we had the plus sign, we had the multiply sign, those were given as axioms. Now we know what that sign is. Good?
Yeah.
And then we'll define division later. So now we know what it means to, what that symbol means. And then we'll also define A minus B to mean A plus negative B. That's what it means. It's shorthand for that. So then we'll define the operation subtraction. But that can't be too far away. It's got to be right around the corner. Oh, next one. Prove that negative A equals A.
So this is all out of the textbook. Everything we've done is in the
Yes.
preliminaries.
I believe so. I might have proved a couple things that he didn't have in there, so I thought some of them I didn't have them labeled what they were. Like, there was only 1 0 on that. I don't have a label next to that, so it might be something I just did, and it felt like he was assuming. So sometimes I'll fill in the blanks with my own proofs. But for the most part, it should be in there, but you always have it on line in case you need to find it. Okay, so we're going to prove that negative a is equal to a. Okay. How are we going to do that? How am I going to show that negative a is equal to a? What is negative a? What's the only information we know about negative a?
That a is negative
That is the number such that negative a plus negative
a. Negative a.
plus negative a is equal to 0.
Oh,
That's what we know about negative a. That if we just somehow add it with negative a, we get 0. So we need to get some negative a in there. How are you going to do this? I mean, we're going to add 0, obviously, because we can't change our equation. But what special 0 are we going to add to that?
Well, isn't it going to be?
And we need negative a in there. How can we get 0 with negative a?
You go negative a plus negative a.
Negative a plus 0 is equal to. Now can I rewrite that 0 with the negative a in it?
Negative a plus a.
Perfect! Is equal to negative a plus
Or negative
a plus negative a. Right?
oh,
Now I'm going to combine that negative a with this negative a to get 0, leaving me just the a.
Right.
You see that?
Yeah,
So, is equal to, you're going to do a lot of steps here to try and make sure you see it all. Put big old parentheses here. We're going to have negative a plus negative a plus a. You see the reordering? We're taking this
Yeah.
and we're grouping it with this term. So negative a, right there. We're grouping this with it,
plus a.
right there, and then we're putting this a at the very end.
Mhm.
Follow everything there?
Yeah. It's so stupid.
So, negative a equals negative a plus 0 equals negative a plus negative a equals, reorder the terms, negative a plus a. This is 0. So that means it's just a. Maybe I should just make sure we see exactly what's happening. I'm calling that group 0. Right?
Right.
Okay. That's our proof that the negative of a negative is a positive. So a negative times a negative is a positive, right?
Yeah.
No, we don't know that yet. This is a multiplication. This is negative a.
Oh, that's right.
That's not negative. What do you mean times? How do I times a negative? That's not a number. That's a symbol.
I see. Yeah.
So no, we did not just show that a negative times a negative is a positive. That is not what we showed. We showed a negative. That the negative of a negative. How can we even say this right?
Negative of negative a.
Negative of negative is positive.
A, the only way I know how to say it is not positive. We don't know that A is positive. A could have been negative in this. All we know is that if we apply the negative operation twice, we're back where we started. So if I take the negative of negative 7, I get back negative 7. If I take the negative of 8, I get back 8. If I take the negative of anything, I get back that thing. That's what we know. That's all we show. So you got to be really careful. Because you might be tempted to think we just showed a negative times a negative is a positive.
So we
It's not
didn't
close to what we
show-
showed.
Did we show that a negative times negative, or negative?
We didn't say anything about multiplying by negative numbers yet. We will use this information to show what we mean by multiplying by negative numbers. But first we need to show that this somehow captures a multiplication by a negative number. Because we want to say that negative a is the same thing as negative 1 times a, right?
Yeah.
That's what we're tempted to say. So let's prove it. And then we can start talking about that way.
Darn, this is advanced calculus. That's what the textbook is.
Yeah, that was our first conversation as to what that advanced means. This advanced calculus does not mean, this is beyond calculus. When they're using the word advanced in this context, they mean you develop calculus. So the idea in calculus courses is you take Calc 1, Calc 2, Calc 3, which is focused on the usage and application of calculus. And then you take what's called real analysis 1 and real analysis 2, which is focused on the development of calculus. What we're doing is more focus on real analysis 1 than on the calculus. Because you'll get the calculus when you go to college. Right? This is we're focusing on proving the things that you're going to be using in college all the time. And proving things that you've been using all the time that no one's ever bothered to prove to you before. Like that negative
This
a
is literally
means.
such advanced crap.
Advanced.
Oh, man.
Tina is literally teaching this in 2nd grade. This right here, she's teaching this in 2nd grade. And I'm looking at here like, what?
Yeah, so that's what we mean. Here, your teachers, when they just tell you stuff. And they repeat it and repeat it, and you eat it up and you eat it up. And you never have a chance to really challenge it. For example, everyone knows that negative times negative is a positive. But then think about that for a second. So you're telling me that if I have negative 7 groups of negative $7, I have $49.
Oh.
What? Why is a negative times negative a positive? Because your teacher said so a lot?
Yeah.
Why is a number times 0, 0?
I thought of that one. That one was stupidly intuitive. $7 times $0.
So yeah, in our advanced class,
That's the money.
for the first time, you're going to learn material you've been talking about since 2nd grade. Isn't that great? Looks like my daughter's going to have a heyday in 2nd grade.
I feel bad for her.
She's going to be all sorts of confused by her teacher. He's like, you didn't prove that. Alright. Let's move on. Next proof that we want to do is that negative 1 times a and negative a are really the same thing. They capture the same information.
I have no negative 1. Where do we know negative 1?
One? Yeah? Negative? Yeah?
Yeah.
So negative 1 is the additive inverse of 1. It's the only number, x, that satisfies 1 plus x equals 0. There's one and only one number that satisfies that, negative 1. That's its definition.
Oh.
That's our definition of a negative number. We proved that there's one and only one number that satisfies us. That's what this whole proof was about. Given any number, there's one and only one number that we can add to that thing and get 0. And our name for that special number is now negativeness. That's our definition of negative 1. So it is now well defined. We know exactly what we mean by negative 1. We mean the additive inverse of the multiplicative identity element.
Yes.
That's exactly what we mean.
Okay.
Wonderful, huh?
Yeah.
Cool stuff. Alright, so let's do this proof. So, we're on this one. This one we kind of do in, well, I'll write it and then talk. So remember that negative a is the number, and the only number, such that when you add it with a, you get 0. Right? So proving that negative 1 times a is equal to negative a is the exact same thing as proving a plus negative 1 times a equals 0. If this is true, then this number has to be this number, because there's only one number I can plug in here that makes this equation true.
Right.
And so if plugging in this number makes this equation true, I must have somehow plugged in a different form of that number.
Right.
Does that make sense what I'm going to do?
Total sense.
Okay. So then let me prove that this statement's true, which is nice and easy.
What is if again?
If and only if, sorry. Good, make me go over this over and over again every time you see it. If and only if means, if this is true, then this is true, and if this is true, then this is true. So they're logically equivalent. It's a different way of capturing the exact same information. Does that make sense?
Yeah.
If you know this, then you instantly know this. If you know this, then you instantly know this. Good?
Yeah.
Okay. So now I'm going to prove that this statement's true. 2. Then a plus negative 1 times a is equal to, can you use the fact that a can be rewritten as
Negative a or negative a.
no, that's not the one we want.
No. Is it gonna be 0 plus a?
No. So I want this whole thing to equal 0, right?
Yeah. Oh, then it's negative a.
No, a isn't negative a. This somehow is negative a. This is still a.
Okay, wait.
Maybe look at this property and that'll give you a hint.
Are you trying to reorder?
Is it?
I'm trying to show that this is equal to 0, but what's the special way I'm going to rewrite this a?
Why is it
1
a
times
plus
a?
negative a?
1 times a, wonderful.
Oh, I'm just
You're looking at the wrong one though.
Oh, did I point at the wrong property?
I think so.
I said this one?
That's the right one.
Yeah.
Oh.
Oh, I see.
Now what are we going to do?
What?
We're assuming
How
twice
can
that
you
you
do
can
that?
do negative 1.
What? We know that a is equal to 1 times a.
Yeah.
That's all I use, going from here to here.
But we don't know that negative 1 times a equals is the additive inverse of a.
No, that's what we're trying to prove.
I know, so you can't just keep using your false information to try and prove something right.
I'm just trying to show what this equals. I'm just seeing what this equals.
Oh, there you go. Okay, I missed that.
So this is the same thing as this.
Okay, there.
And I'm trying to prove that this is equal to 0. So how am I going to get 0?
I need to look.
What?
Trying to get 0 here.
Okay, it's going to be your x plus y equals 0. You're going to use that.
No.
Wow.
I'm going to use number 9. How can I use number 9 there? Imagine number 9 except for we flip the equation around.
Okay, so you're going to pull your a out.
Pull my a out.
Yeah.
So now I've got a times 1 plus negative 1. What's 1 plus negative 1?
0.
0 by definition, right? So that's a times 0. And we already proved a times 0 equals what?
0.
0. Okay. So a plus negative 1a equals 0. That's what we want to show. We're done.
There's only one number that can do that, and that's negative a.
Yeah, there is only one number that.
Yeah, what?
You didn't state it.
I captured the information right here and I talked it when I said it. So, look. There is only one number I can plug in right here, such that a plus that number equals 0.
It has to be.
There's one and only one. We proved that. We call that special number negative a. Now, there's a lot of different ways that we can write that negative a. For example, we know that's a different way of writing it. The question is this somehow a different way of writing that negative a?
Yeah.
That was our big question. Is this somehow negative a?
No.
So if this equation is true, then this is somehow negative a.
Right.
So then this is equal to negative a. Do you understand?
My question is, on number 2, when you first, yeah, right there. That is not 9.
Now, going from here, I was trying to get you to see if we could put a 1 there and factor out the a.
Okay.
That's what I was trying to get you to see. So I thought you were seeing it when you suggested we rewrite that as 1 times a.
Okay.
But here's where we factored. And we got our 0. And we got 0.
Yeah,
F.
No, that's a W. But pretty close. It's a win, right? Did you hear how she's trying to grade my work? Jeez. Alright, let's move on. Okay, the next thing we want to prove is, this one's a little bit harder to just motivate on the fly. It's just going to help us with other proofs as we go. But it's the proof that negative AB is equal to negative A times B.
Okay, wait, what?
What's it?
So remember, A times B is just a number.
Mm-hmm.
I'm saying if you take the additive inverse of a product, that's the same thing as taking the additive inverse of one of the numbers and then multiplying it by the other number. So I'm saying negative 6 times 7 is the same thing as negative 6 times 7.
You can
That's
say
what I'm
that-
trying to prove.
You can say that for negative B, right, though, too.
Well,
If A was positive and B was
right, I could have flipped the order here,
Okay.
which then does that, which then gives me it. So we don't need to specify for both of them. See what I mean?
Mm-hmm.
Okay. So you understand how this is something that still can be challenged and we need to prove it?
Yeah.
Okay. Now we're going to reference our past proofs for this. So
Excuse me, observe that
from this one,
Yeah.
yeah,
negative 1 times a.
and as a common way to do these proofs, sometimes you pick a side and then you manipulate it until it looks like the other side is a common way to do it, right? So that's what what we did up here. We started with that and we kept messing with it until we got that out. Common way to do it. So I'm going to pick one of these, doesn't really matter. I'm just going to pick the left one. I'm going to keep manipulating it to see if I can get it to look like that. Okay? So observe that negative A times B is equal to,
Negative 1 times a times B.
perfect, negative AB is equal to negative 1 times, maybe I'll do parentheses. I'm kind of using and not using my dots randomly, but hopefully you understand every time I'm doing a multiplication, right? Okay? Then what?
Okay, so we're gonna need to.
Yeah, use, well,
associative.
use 6. Okay.
Associative,
We're
Is that
gonna
what you're
need to
saying?
group A with
the negative
the
1.
negative 1, and not the B.
So we want the negative 1 grouped with the A and not the B. Okay?
Isn't that it?
No.
That's the associative property.
Negative A, B, right?
We use the commutative. Oh, we just used the associative. We didn't use commutative.
Yeah.
Okay.
No, and then you use the one up there and
Now we use this one
that's
again. Right?
Yeah.
A negative A
That's
times
why I
B.
said you had it.
Which is equal to negative A times B. So from here to here, we reference this proof,
Mm-hmm.
manipulate, then we use this proof again to get from here to here. And we're done. Something is jabbing my foot. It's not feeling anything. Weird. I just randomly made it to my sock. Check that. Oh well. see. Next we want to prove that a times b is equal to negative a times negative b.
Say that one again.
A times b is equal to negative a times negative b.
Dude, I'm gonna find a way to this
My good hell.
Is it after the preface?
I just took so much for granted that I just want to go back to simpler times.
It might be in the.
How does it get simpler than this?
Oh, and you just take it for granted.
Yeah, you've been operating on like a massive list of assumptions. Now you can reduce that to just 10 assumptions. That's all you need. You need those 6 trillion assumptions you've been operating on in life. Maybe some of them were bad. Nice short list, right?
Okay, this one. We're going to want to make negative a, and then we're going to want negative 1 times a times negative 1 times b. And then you want to factor out negative 1. Or factor out, yeah, the negative 1 of the a times b.
Let's see. So first thing we're going to want to use is this one, obviously, to get our 2 negative sides in there. So I'm going to start with this. I'm going to use this one to get my 2 negative signs in there.
Don't start with the right.
I could have started with the right, and I could get my 2 negative signs out of there, and then use this. Or I could start on the left, get my 2 negative signs in there, and then redistribute them here. Either way is fine. So 1, a times b is equal to negative a times b, right? Is equal to, let's see the order I did this in. Ah, right. And that is equal to negative. So first thing I want to do is group this negative with just the a, right here. So that's negative a times b. And then I want to get the b in front, get the b out of there, and then do the same thing with the b. So then that is equal to negative b, negative a. And then doing the same thing we get negative b, negative a. So I'll re-walk through every step. So we see where I came from and where I went. So starting with a times b, we get our 2 negatives using this, right? Okay? And then we have negative ab here. Using this proof, negative ab is the same thing as negative a times b, right? Swap my orders, so it's b times negative a, and then use this again. Negative b times negative a is the same thing as negative b times negative a. Swap my order again, and that's what I was trying to show. You follow it?
Yeah.
No, I'm missing you right there. Right where you switch it.
From here to here?
No,
From here to here?
yes.
So
No. From there to there.
from here to
Yes.
here. So I have negative
Mm-hmm.
b times negative a. So I have negative number times number. I have negative number times number.
That means you can just make a negative first number.
So I can now apply the negative to the first of the product. So I have negative number times
Oh,
number.
okay.
Apply the
I
negative
see
to the
now.
first of the
Or
product.
negative a is just
Okay,
a number.
I
Don't
see
think
now.
of it as negative a.
Yeah, we just have some number that could have been an x. Negative b times x is equal to negative b x.
Okay, I see it now.
Does that make sense?
Yes.
Make sure you understand these. I mean, this is as easy as this class is getting. Let's
Losing
say
you
that.
right there.
Yeah, that's fine. Getting lost isn't bad. Never taking the time to get found, that's just stupid. So, make sure we're all found.
Are we going to go through interval notation?
Yes.
Dude, aren't we almost done with the preliminaries?
No.
Yeah.
Yeah, that's what I'm telling you. The author gives you almost nothing.
I guess we still have to prove inverse
All right. Next, we're going to prove that 1 is equal to negative 1 times negative 1. Right?
Yes.
So 1 is equal to 1 times 1, right? Is equal to negative 1 times negative 1, using our last proof.
Yeah.
A times b is equal to negative a times negative b. 1 times 1 is equal to negative 1 times negative 1.
I would say
Why did we prove?
Oh,
Why did we prove that?
because like it's a little bit different than that. That's two values times each other.
This is called a lemma, or this is called a corollary. Sometimes when something just instantly falls from another proof, and we just call it corollary, and we show it real quick. Why do we show this? Because we use it so much that we better make sure you understand it for sure. That negative 1 times negative 1 equals 1. Because this is slightly different from this. This doesn't tell us that 1 equals negative 1 times negative 1. That told us only this part.
I have a question.
So we need to link that with that to get this.
Right now in our
So it's a small
knowledge,
step, but still we gotta take it.
right now in our knowledge math, we only know two numbers, right? 0 and 1, and negative 1. Because that's all we've ever used, as far as numbers.
As far as numbers, well, no. Because you have 1, right?
And 1 makes the whole number.
Well, no. We're guaranteed that you can take any two numbers and add them together.
Oh, yeah.
So we know that there's also 1 plus 1. Whatever that is, we have a special name for it we call 2, but it's just 1 plus 1. It's another way of writing it. And then we can also add 1 to that real number, and add 1 to that real number, and add 1 to that real number.
And you can time those numbers together.
And then you can start multiplying those numbers together as well. And then once we talk about the multiplicative inverse, that starts giving you fractions. And then you're able to create every rational number. Now, it still doesn't give us the irrational, so this doesn't give us all the real numbers yet. But
So
we're well on our way.
We're going to prove an irrational number.
Yeah, the real numbers includes irrational numbers. And we don't have our axiom that gives us that yet. That's called the completeness axiom. And
So
we'll get there.
what we're doing right now is just showing what the real numbers are.
Yeah, we're showing what
And properties.
we're showing properties of the real numbers. That's all we're
Those
doing.
are all the axioms?
Not all of them. No, there's the positivity axioms, which tells us which numbers are bigger than other numbers. And then there's the completeness axiom, which finally gives us irrational numbers.
So those are the two.
The positivity axioms, there might be a couple of them. There's 2 positivity axioms, and then there's 1 completeness axiom.
So that
So
was
11 axioms,
13.
or let's see, 13 axioms in all. For the real numbers. That's
To
it.
find every real number.
To completely talk about the set of real numbers. This whole class, we've only used those 13 axioms. That's
We
it.
use imaginary in calculus, right?
When you get to complex numbers. But this class, we're focusing on the real numbers. Calculus, they come and go. You kind of talk about them. That's a separate field. Just like there's real analysis, which is linked to calculus. There's complex analysis, which you can have calculus in that with complex numbers as well. We're not going to deal with complex numbers very much. If we deal with them at all. I don't know. We'll see. I haven't gone through this textbook yet, but the author did. I barely found it. I was asking around for recommendations from a bunch of my teachers, and came across this one, which tried to do what I wanted. What I was really looking for was a textbook that went through calculus, but went through it thoroughly and proved everything that they used and required the students to prove things. That's what I wanted, and I couldn't find it. This was supposed to be that. The more I get into it, it's not really that. It's more just proving and requiring the students to prove, which is why when we're done with this book, we're going to go to a regular calculus book after we've proved it all.
Are we going to do any proofs in the regular?
I will. I don't think that the author ever requires you to prove anything,
It's
which is what I hate.
application.
Yeah. So,
Yeah, this book is so long. Like, what if we don't finish this book?
we're not finishing this book.
Oh.
We're just going to integrals and then we're done. No, you can't do this whole book because you haven't had linear algebra.
I'm already at integrals. There's like 2 chapters.
Integrals, I think, is chapter 5 or 6, and we're skipping a chapter.
Oh, I look at sequences.
We're skipping chapter 5, I think, which is differential equations. We're also not going to worry about those. So we're not going to worry about complex numbers, not going to worry about differential equations. Just going to get to differentiating and integrating, and then...
We're not going to do differential equations.
Yes.
No, we're gonna in the second half of the semester.
In the second half of the semester, I'll be mindful to get to integrals.
Really?
Yeah.
What?
It's going to take a long time to get through all this.
Dude, we got the integrals in like the first semester.
Yeah,
No,
but
we got
Ariel
to-
does calculus
We
different.
did differential.
What?
all
Why
first.
would you teach us calculus?
And we did
Why teach us
integrals
integrals?
also.
Integrals is like the main part.
Oh, we'll prove integrals. I don't know if we're going to get to applications of integrals. That's the
No.
last thing that we're going to cover in this class.
We did integrals.
So we're gonna
also.
prove derivative? Because
Yeah.
Ariel did prove derivatives, right?
Yeah, he proved them first week.
Yeah, chances are he gets up there and he gives you the theorems and derives it for you. But I wanted something that requires the students to over and over again prove.
We're gonna prove derivatives.
Yes. You're going to prove, for example,
Dude,
I want
that was intense
to
crap.
prove stuff like x squared equals 2x. I want you to prove that. I don't want you to say that. I don't want you to use a formula to give me that. I want you to know right out the door how easy that is to prove. I want you to be able to prove right out the door that the integral of x with respect to x is equal to x squared over 2 plus some constant. I want you to be able to prove these things, and I want it to be easy and obvious to you. As easy as proving an even plus an even is an even. That's the
We
kind of stuff I
proved
want.
He did. Ariel did.
Ariel did. Every textbook has a teacher do that. They have the theorems, and the teacher goes through the theorems. But then the student's never required to do anything with it. They learn the theorem, they understand it right there in class. 2 weeks go by, the student couldn't tell you the definition of an integral, let alone any theorem about the integral to begin with. It's gone. It goes in one ear, out the other. And I hate that. I resent that. Because they focus so hard on application. I have never in my life come across some student in math who understood the theory but struggled with the application. I could throw a dart in the math department and hit a student who understands the application but can't do the theory to save his soul.
That is actually very encouraging.
But if someone understands, if you understand these proofs, the chances of you struggling with basic arithmetic again, it's not going to happen.
So you think if I can prove an integral, there's no way I'll have problems with my integral problems on that?
I'm saying that if you are able to prove something like x squared is equal to x cubed over 3 plus some constant, if you're able to prove that, then when this comes up in different contexts, in different applications, it's not going to be hard for you to apply it. So when you take physics, for example, if you go and you take electricity and magnetism, over and over again what your brain has to do is look at the real world and see how the integral applies. And it's based off of the definition of an integral. And you do that over and over and over again. And students struggle with that because they don't understand what the definition of an integral is. So when it comes up in a particular context, they can't find it. They need the teacher to give them it already set up how they're used to seeing it already, and then they can solve the integral. But to go from what's going on in the real world to find the integral that fits the definition for how they're applying it, and then calculating it, there's just not a chance. So what I'm saying is if you can prove this, then you're never going to struggle with this type of integral again.
I did.
But you'll still struggle with other types of integrals. Integrals are notoriously difficult. For some reason, it's so much harder to integrate than differentiate.
Really?
Yeah, and there's several integrals that you can't
inverse.
Yeah.
prove. I know, interesting, huh? Anyways, we'll get to all that. Let's see if we can get through the preliminaries. Alright, and now is when I finally introduce the definition. Definition. That is logically equivalent to A plus negative B.
So we're finally getting the minus signs here.
So now we can start proving things about subtraction. So let's do a proof of subtraction. Let's prove that A times B minus C is equal to...
Wait, we already proved subtraction?
No, we barely defined it.
Bro, we barely got a negative sign.
Okay, what is, so definition isn't proving anything.
No,
Well, hold on.
the definition, so theorems give you new information, proofs give you new information, stuff that you didn't already know. A definition takes something that you already know and gives you a shorthand for it. Something that you already stand in just gives you a shorthand for
Figure
it.
at it.
I mean, think about a dictionary. When you look up a word in a dictionary, it gives you a short one word that means a whole bunch of words. That's what it's for. You already know what all those words mean, and now you can just use that short word to capture that meaning.
Okay.
That's what we're doing. This is shorthand for this.
Okay, so as soon as we prove this, doesn't that add what the subtraction sign can do? This is proof.
This proof?
Yeah.
Well, this proof is, we're just saying, the same way that we do distribution this way with the plus sign, turns out we can also do it with the minus sign.
That's what we're saying.
That's what we're going to prove, yeah.
And then it adds to our definition. What is it?
It doesn't add to our definition. Our definition of subtraction is our definition of subtraction. We say if we use this symbol this way, then we can also use it this way. And we can also use it this way, and we can also use it this way. Right? Because that's what we did over here. We said, look, these are the ways that we can use plus and times. And now we can also use them all these ways. And then we came across this negative symbol. We said, here's our definition for what that negative symbol means. Now how can we start using it? Well, we can also use it this way. Now we come up with our subtraction operation. Takes two numbers, spits out a number. We define what that means. Now we're seeing how we can use that subtraction operation. Same thing. Good?
Uh-huh.
Alright. So, how are we going to do this? Now that we're using a definition, you can start doing what I talked about when we were talking about proving evens. Unravel the definition. What is the definition of that? So observe that A times B minus C, what's its definition? That is A times B plus negative C. That's its definition.
Yeah.
Right?
Yeah.
So use its definition. Now we can use our distributive law. That is AB plus A times negative C. Right?
Yeah.
Mm-hmm.
And now we can use this guy. We're going to pull the negative out this time. Notice I could swap those orders, pull the negative out, swap the orders again. I'm going to do that all in one. So that's AB plus, or not plus, minus AC. And we're done.
That's cool.
Sorry, I skipped a step. That's really what I should have written, right?
Yeah.
We swap those and we pulled our negative out,
Mm-hmm.
but that doesn't mean I can get rid of the plus. Now I use my definition of what that and that are the same things. So now I can rewrite that. Sorry, I shouldn't skip that step. Good?
Mm-hmm.
You understand why from here I need to go to here, then to here?
Yes.
I couldn't just instantly get rid of that plus sign. The only way to get rid of that plus sign with a negative is to use this definition. This definition says you can take that plus and negative and rewrite this way for minus. Plus and negative is minus. Okay? Good. Let's see. Prove that negative b minus c is equal to negative b plus c.
Oh. Switching up on us.
Switch it up. Alright, let's do it. We've got negative b minus c. Use the definition. What does that equal?
Negative b plus negative c.
Right?
Yeah.
Now what? I really want to somehow distribute
Yeah,
that negative
whatever.
sign, but I only know how to distribute numbers. So how do I get that to a number?
Change it to negative 1. Wait.
Change it to negative 1. Use this.
Okay, yeah.
So we have negative a can be rewritten as negative 1 times a. Right? So this is negative 1 times a. Now we can distribute, right? Which is equal to negative 1 times b plus negative 1 times negative c. It's one of our axioms. X times y plus z is x times y plus x times z.
That seems like a big leap.
It's not a leap.
Well,
It's,
that sounds like a big assumption.
we have to have something that tells us how to combine multiplication and addition. We have to have something that tells us how we can use those things together, otherwise we never know how we can use them together. So this is the only thing that tells us how we can use them together. So that has to be an axiom. Because maybe I should be distributing my plus over multiplication, not my multiplication over plus. Or maybe they should operate some different, who knows? Because for these exact same symbols, if I slightly change these axioms, then they start giving us properties that other symbols you already know have. For example, matrix multiplication does not follow the same multiplication that this does. And if I change my axioms, I might accidentally produce matrix multiplication instead of this multiplication. Right. Anyways, so that gets us to here, right? Now we can use this on this, which gives us -1b plus 1 times, right?
Yeah.
And then this, we can use this, right? So that's equal to -1 times b plus 1 times c, I guess, I'll rewrite. And if I had to get rid of my 1's, -b plus c. See it?
Yeah.
Any weird steps, any questionable steps? Anything you want me to go over again?
Are you using that top proof for when you do -1 times -c?
For right here,
Yeah.
this step to this step is this proof. -a times -b is a times b. -1 times -c is 1 times c. That make sense? Anything else?
-1 times b equals 1 times b.
-1 times b equals -1 times b.
Yeah.
Yeah, but you could X out that whole step in the middle.
No, you couldn't.
Yeah, you could because of this, and that is this. So you could literally just write it.
Yep, we could have used this one.
So you could have just X out that whole middle step.
Wait, yeah. Instead of using that one.
Yep,
And save yourself time. I don't know.
save yourself a step. And that's an important point that was brought up in my discrete math class. I don't know that it's been brought up in this class yet. There is no one way to prove things. There are several proofs of the exact same thing. But here's what's not possible. It is not possible for you and I to operate on the same assumptions and prove contrary results. Right? So you and I might have different proofs of the same thing, but it is impossible for us to both have valid proofs starting with the same axioms, coming to opposite conclusions. So while you may have different proofs, you shouldn't be able to come to different conclusions. Otherwise you have an invalid proof. Does that make sense?
Yeah.
Okay. Good with that proof? Let's move on to the next one. Oh, shoot. I never defined that. skip over my definition of the multiplicative inverse? It's probably one of the problems that the author has you do, and that's why I skipped it. So, something that we're going to use that we didn't prove, and I bet it is because it's very similar. So one of the things I think you're going to prove is that right here. So let's look at this one for a second. Remember that we proved that for all x, there is one and only one y such that x plus y equals 0. Okay? I think I require you here to show that for each x not equal to 0, there is one and only one y such that their product equals 1.
We've only proved that there is one. Yeah.
Well, here we know that there is one. We didn't prove it. It's an axiom. But I think in the homework I'm going to require you to show that there's one and only one. That satisfies that, okay? And so we need our definition that I'm going to use real quick now. Make sure you understand me.
Yeah, for us to prove we need this whiteboard.
No, you got your paper to turn into one. Definition. Let me see how I did that. Given A in R, A not equal to 0. Good? Then A inverse is the unique number such that A times A inverse equals 1. Right? Very similar to the definition of negative. So now we've got our inverse. Okay, so now I'm going to do a proof with the inverses.
Wait. Just another way to write it, right? That's what definitions are.
Yeah, just another way to write it. So you're going to prove in your homework that there is only one number that I can multiply by A to get 1. And then we're going to call that one and only one number A inverse, A to the power negative 1. A inverse. And that's called its multiplicative inverse, just like that was called the additive inverse. And the same way that we use the additive inverse to define subtraction, we're going to use the multiplicative inverse to define division. But for now, let's just do a quick proof. Proof.
More whiteboard space.
I'm going to need 2 lines here, I think. So let's try small enough I can get to lines. Proof. Need to prove that the multiplicative inverse of the multiplicative inverse is A. Same way, very similar to this proof. Okay?
In order to do that, I think you need to rewrite your A.
Yeah, so we need to show that this is equal to this. So let's start with it. A inverse inverse. And we need to keep messing with it to make it equal to A. And we're going to use the exact same strategy. The same way that we started with this, and then we added 0 to it, and then we got that 0 to be the special 0 that we wanted, and then canceled out to get A. We're going to take this, we're going to multiply it by 1, we're going to use a special 1, that means that we can cancel this out and end up with just an A. You with me?
Yeah.
Okay. So this is equal to 1 times A inverse inverse, right? Now write a special one. The special one that we're going to write is A times A inverse times A inverse inverse, right?
Okay.
Now I'm going to group this A inverse with this A inverse inverse, leaving the A by itself. So that is equal to A times A inverse times A inverse inverse. And what is A inverse times A inverse inverse?
We don't have anything to say.
It's 1!
We don't have it.
Yes, we do. That's our definition. Given A inverse is the number that makes our product 1. Given A, which is A inverse,
Right.
then A inverse is the number that when they multiply together, you get 1.
Yep.
Right? We're saying that symbol says, I am the multiplicative inverse of whatever came before me. So this is the multiplicative inverse of whatever's in that parentheses. That is what was in that parentheses.
Right.
So those things together is 1.
Mm-hmm.
Okay? So you're not confused by that chaining. Alright, perfect. So that equals A times 1 equals A. Boom. Box it. Good? Alright. So feel free to take a break. I'll erase the left whiteboard and start writing the rest up there. So you can take a break while I do all this writing. We've got 1, 2 more pages of notes.
How many have we done?
Today?
No. Oh, yeah, today.
Today we've done 1.5. We've done close to 2.
You can do it.
Well, if they're as simple as this, then really the majority of it was this size.
Hopefully you guys are comfortable enough with these axioms now that I can get rid of them.
No.
They're in our textbook.
We'll probably be referencing proofs at this point more than axioms. You want me to take a break?
Adam, why didn't you get me one?
You want one?
Yeah.
Here.
You know, I've done so funny yesterday.
What did you just say?
They're playing Halo. Check this picture out. I said, oh god. It's 4:41 a.m.
Oh. I thought they were watching the game.
Yeah, so was
What are we watching?
They're playing Halo.
well, that be
Oh, I lost.
Look how many beer cans are empty.
Is that Lizzie?
Look at this. It's actually nice. Spoon. Yeah.
Are you watching a TikTok?
Someone posted on their story.
Was it Joseph? Because, yeah.
She go hang it up for Uncle Lon.
Hang it up.
Go hang it up.
Now I want my senior thesis to make a map of where the worm has been.
And
Speak that with me. In that classroom.
Yeah, exactly. Just for done.
Just forgotten.
Alright, we ready to continue?
look at this. When the Christians were getting persecuted at the peak of it, that's when the gang robbers were at their peak. Or close to their peak.
Where, when the Christians were, you mean like from the Romans?
Yeah.
Oh. Dude, look at the way the judges, bro.
Yeah.
That memories. Where's Stephen? Oh, yeah, he's right in the middle. Oh, I do not want to do that presentation.
Alright, let's continue. Finish that page of notes. We'll only have one more page after we cover this. Where you going, James? Oh. You don't like the world to hear me?
Yeah, I want to hear them.
By the way, you made my sister Esther jump. Yeah, last week. She was in office suite and she was like, she's super jumpy, but she heard you scream and she jumped so high apparently. I was like, dude, what the heck?
Alright, let's continue with talking about this multiplicative inverse for a sec. Right? What's the multiplicative inverse of A? It's a number such that when you multiply A by it, you get 1, the unique number. So now let's look at the multiplicative inverse of A times B. We're going to prove that that's the same thing as a multiplicative inverse of A times a multiplicative inverse of B. You understand how these two are different?
Yeah. Very much so.
Yes.
The same way that negative AB is not the same thing as negative A times negative B. And we had to do a proof of that somewhere over
Yes.
there. Oh, that's not true.
This symbol
No,
does not mean
isn't
the
it?
exponent,
Yeah,
right?
so not the exact same. Huh?
This symbol doesn't even closely even resemble an exponent.
It does resemble an exponent, but we don't know what exponent is yet.
Okay. So eventually we'll find out what an exponent is and say, oh yeah, this is the same thing.
Yeah, they capture the same idea. The multiplicative inverse of A and A to the power of negative 1 thought of as an exponent are logically equivalent. So there's a reason we use that notation. Okay, anyways, so let's do this proof. Now, here's how we're going to do this proof. What is AB inverse? It is the unique number such that if you multiply this by AB, you get 1.
Yeah.
Right?
Mm-hmm.
So, AB times something equals 1. The only number that satisfies this is this number. So if this number also satisfies it, then those two numbers are the same number.
That's jumping, isn't it? Listen.
Okay.
There is one and only one number I can take AB and multiply by to get 1.
Right.
What is that one number I can take AB and multiply by to get 1? That's this number.
Yes.
So if AB times this other number also gives me 1, then those two must have been the same number. Yeah.
Mm-hmm.
Yeah.
Good with the logic there?
Yeah.
So instead of trying to prove that this is equal to this, I'm going to show that this is equal to 1. And that's logically equivalent.
Right.
Good? Okay, so this is what we're going to focus on. So then AB times A inverse times B inverse. You use the associative and commutative properties to distribute them the way you want. That gives you 1 times 1 equals 1. Sorry, I kind of skipped some steps there. But do you understand everything that we did?
Yeah.
Yes. Yes.
Just rearranging it.
So from here to here is just rearranging and grouping terms, how we want,
Okay.
which is just using associative and commutative properties.
Just 1 times.
And then A times A inverse is,
One.
B times B inverse is, 1 times 1 is,
1.
okay. So those were all the leaps I made, sorry. Should have written a couple more steps there. You good with it?
Mm-hmm.
Alright. Next, our definition of division. So if we have A and B and R with B not equal to 0, then A times B we define to be A times B inverse. So we just defined what we mean
Why
by
do we
A
add
divided
that
by
B
B.
not equal to 0?
So we were only guaranteed on one of our axioms. So what it said is for all x, where x is not 0, then there is a y such that x times y equals 1.
Mm-hmm.
So, in other words, I'm only guaranteed that x inverse exists if x isn't 0.
Oh, yeah.
So, over here, I want to define using b inverse. The only way I'm guaranteed b inverse exists is if b is not 0.
Right. There we go.
Does that make sense?
Yeah.
So it follows from that axiom I erased.
Good, because I
So
thought you were
is this-
making me
is this
jump
where we're
on
getting into
that
division right
divided by 0
here?
is undefined.
Right, it is undefined. There's a reason that we set the axiom that way. And the reason that we set the axioms that way is because when you try to divide by 0, you do get something undefined.
Okay, so this is where we're getting into division.
Yeah, we just made it define what it means to divide. We just gave it a definition. A divided by B means A times B inverse. So what is 5 divided by 4? That is 5 times 4 inverse. Which is, if you know already, 5 times what's the multiplicative inverse of 4? 1/4.
Oh, okay. Okay.
Or maybe you would have liked times 0.25, or whatever. That's what we mean by 5 divided by 4.
Okay.
So that's the definition of division. Just like our definition of subtraction was add the multiplicative inverse. That's what we mean by subtract. What do we mean by divide? Multiply by the multiplicative inverse. Add the additive inverse, multiply by the multiplicative inverse. Lots of symmetry. Good?
Mm-hmm.
Alright, so let's do a quick proof with division now. Let's prove that A plus B divided by C is A divided by C plus B divided by C. Okay? This is just using the distributive property. A plus B divided by C is by definition this. That's its definition.
Right.
Mm-hmm.
Distributive property.
Yeah.
Definition of division.
Yeah.
We're done. Alright, positivity axioms. These guys are real upbeat. 1. If A and B are positive, then so is A plus B and A times B. So that's something you prove. This is an axiom. This is an assumption.
Positive.
You mean you
Okay, great. Positive is not a defined term. This is one of these undefined terms. Postulates and axioms give meaning to our undefined terms, just like in geometry. You never defined a line, but you had a postulate that every line contains 2 points. We're never going to define positive. But if A and B are positive, then so is A plus B and A times B. If you have a line, there's 2 points on the line. We still know what a line is, we still know what a point is. We still know what positive is. It just means that,
Have we defined negative?
Can we define negative?
yeah, we can define negative.
So if we can define negative, how come we can't define positive?
We use positive to define negative,
Right.
Oh, okay.
Negative is not positive.
right? You use your undefined terms to create definitions. It's one of the things that you use to create definitions. is
Okay,
your
but
undefined
why
terms.
can't we prove that? Because we can't
Positive.
define positive.
Because what are you going to use to define positive? Negative? No, you use positive to define negative. What are you going to use to define positive?
Oh.
Are you going to say all the numbers greater than 0? No, we're going to show that all numbers greater than 0 are positive. But what do we mean by positive?
Not negative.
No, because they're 0 also, so that doesn't work. Because 0 is not negative or positive.
Well, then you just say non-negative.
But negative also uses the definition of positive, so you can't use negative to define positive. We use positive to define negative. So if A and B are positive, whatever that means, so is A plus B and A times B. We don't prove it, we assume it. Second assumption. For all numbers, either A is positive, then A is either positive, or negative A is positive, or A is equal to 0. One of those 3 things and only one of those 3 things is true. Sorry, bad verbiage here. I should have written it better. But if you pick a real number, one of 3 things is guaranteed. Either that number is positive, that number is 0, or that number's additive inverse is positive.
Why do we need to know positive?
It's going to give us ordering. We're now going to be able to say one number is bigger than another. We can't do that without positive. You don't want to say 10 is greater than 5. How are you going to say that?
10.
The way you're going to say that is 10 minus 5 is positive.
Okay.
You see what I'm saying?
Yeah.
So we're going to use positive to give us, essentially what it's giving us is ordering. Good? So the field axioms that we went over so far, that gives you in mathematics what we call a field. When you add the positivity axioms, then you get what's called an ordered field. Order now makes sense. So this is giving us order, essentially.
Okay.
That you can you can put 1, 2, and 3 in order. Okay. So those are our 2 axioms. Make sure that makes sense. If A and B are positive, A plus B is positive, and A times B is positive. So the sum of positive numbers is positive, the product of positive numbers is positive. That's axiom 1. Axiom 2 is, for every real number, it's either positive, or its additive inverse is positive, or it's equal to 0. One of those 3 things has to be true, and only one of those 3 things is true. Does that make sense?
Mm-hmm.
Great. And we can come up with a definition. We can say if negative A is positive, then we define A to be negative. And that could be our definition of negative. Right?
Mm-hmm.
And there's a definition for negative. Anyways, so now let's define symbols that we like. What do we mean by A is greater than B? That's how you read that, right? You've seen the symbol a lot, you're comfortable with it.
Mm-hmm.
So let's define what all these different symbols mean real quick. A is greater than B, what does that mean? That means the number A minus B is positive. A is greater than B, logically equivalent to A minus B is positive. Good?
Mm-hmm.
A is greater than or equal to B is logically equivalent to A is greater than B or A is equal to B. A is less than B is logically equivalent to B is greater than A. And A is less than or equal to B is logically equivalent to B is greater than or equal to A. If you remember doing this in geometry, we had a heck of a time going from this to proving that if this is true, then this is true. So we just had this and this in geometry, and then we proved these other ones from it, but we're going to take those as definitions in this class to save us a hassle. Oh, no, we didn't. we define each of them, and then we show that if this is true, then this is true. Never mind. Who cares? Who cares? Forget I had all that. Sorry. Bad tangent. So there we go. So we got our positive axioms and the definitions that we use with positive a lot. Greater than, equal to, less than, or equal. Any questions about what any of those symbols mean? So let's do a quick proof. Let's prove that the square of any non-zero number is positive. So for all real numbers not equal to 0, then a squared is greater than 0. Notice, a squared greater than 0 is the same thing as a squared minus 0 is positive. Right? That's the definition of that greater than. A squared greater than 0 is the same thing as a squared minus 0 is positive, is the same thing as a squared is positive. So notice that saying a squared is greater than 0 is the same thing as saying a squared is positive. Okay? So notice how this is already forcing our numbers greater than 0. These axioms are already forcing our numbers greater than 0 to be positive. Okay? But let's go over the proof. So 1. Since a is not equal to 0, then one of two things is true.
Wait, we haven't defined square.
We haven't defined square. You are correct. So I can't remember the author's exact note on this. He puts a note in there and he puts a definition in there, and I forgot to write it down. But in short, the definition he gave so far, I'm glad you brought this up. Definition he gave so far is basically a to the n is equal to a times a times a n times. And I don't think we have a to the 0 defined yet. Shoot. So we'll leave it with this so far. So a cubed is equal to that. And then I'm going to have to remember to go look at that and see what exactly he says. But it's in there somewhere. So good catch. So a squared, what do we mean by a squared? We mean a times a. Good? Alright. So let's go over. Since a is not equal to 0, then one of two things is true using axiom number 2. Either a is positive or negative a is positive. Right? That's what axiom 2 tells us. All real numbers are either positive, or their negative is positive, or that number is 0. Since that number is not 0, then that only leaves 2 more cases. Good so far? So let's handle each case. If a is positive, then a squared is positive. How do we know that? What?
Because the number times the number is.
Yeah, number 2.
A positive times a positive is positive. Okay. That was axiom 1. A positive plus positive is positive, and a positive times positive is positive. So, since a is positive, a times a is positive. And so, a squared minus 0 is positive. Right?
Yeah.
Because, maybe I should have written, and so a squared is equal to a minus 0. A squared minus 0 is positive, right? Because that's the same thing as that. You with me on why a squared minus 0 is positive? Because it's just a squared, and a squared is positive. And a squared minus 0 is positive. That's the definition of a squared greater than 0. A greater than b means a minus b is positive. So a squared greater than 0 means a squared minus 0 is positive. Good? Alright, so that handles the first case. Now let's look at the second case where negative a is positive. If negative a is positive, then negative a times negative a, which is a squared, is positive. So a positive times a positive is positive. So we know that this is positive. And we also know we can write that this way. How do we know we can write this way? This one. Negative a times negative a is just a times a is a squared. Good? So if negative a is positive, then a positive times a positive, which can also be written this way, is positive. which is the same thing as a squared minus 0 is positive. Therefore, a squared is greater than 0. So, in both cases, a squared is greater than 0. So the statement a squared is greater than 0 is always true when a is not 0. And so we could make that a stronger statement, and we could add to that. Well, you know, I'll just leave it at that. That's good. Now, a corollary of this that follows real quick. 1 is positive, or 1 is greater than 0. Same thing. 1 is positive, 1 is greater than 0. How do we know? 1 is equal to 1 squared. 1 squared is greater than 0. Using this. For all numbers a where a is not equal to 0, a squared is greater than 0. 1 squared is greater than 0, which is equal to 1. So we now know that 1 is greater than 0. Crazy, huh? Good?
Yeah.
Alright, that's where we are so far. Three more proofs. And then interval notation. Let me go through interval notation first, and then I'll just cover however much of the proofs I can cover, because they're in the appendix so you can look at them. And then that way we can be officially done with the preliminaries. So, interval notation. Sorry to kind of jump gears on you like this, back and forth, but I want to make sure we get through it all. Integral notation. So, let's define explicitly what we mean. Integral notation. Given a less than b, I'm going to define a bunch of sets. So, the set, or the interval AB, is equal to the set of all x such that a is less than x is less than b. A, b like that, is equal to the set x such that a is less than or equal to x is less than b. A, b like that is equal to the set x such that a is less than x is less than or equal to b. This is not a list. This is not an ordered pair. And you just have to know from context what we mean. So we use the exact same notation for an ordered pair as we do for an interval, which is unfortunate. You're just going to have repeated notation as...
It should be obvious.
Right? Because sometimes it means that. Sometimes we use parentheses when we're talking about like the distributive law. And then sometimes we use it to talk about an interval. So this is representing a set of numbers. This is not representing the ordered pair A, B. Does that make sense? Mm-hmm. Okay. Then we have A, B like this. That is equal to the set of all x such that A is less than or equal to x is less than or equal to B. We have A like that is just a set containing A. Let's see.
Probably.
And all my infinities.
After you download something on your phone, where do you find it?
What?
After I download a PDF on my phone, where do I find it?
Yeah, an iPhone? Goes, I don't know. Goes straight to books on an iPhone.
I just downloaded a
How
PDF.
to find a PDF on Samsung.
There should be a downloads app.
Here's a summary from WikiHow 10. Part 2 opening downloaded PDF files. 1. Open Adobe Acrobat Reader. 2. Swipe through the tutorial. 3. Tap Get Started. 4. Tap the Local tab. 5. Tap Allow when prompted. 6. Refresh the page. And 7. Select your PDF.
That's exactly what I did.
Open Adobe Acrobat Reader. So you just have an app.
Yeah, you have to download Adobe Acrobat Reader.
That's stupid.
less than b. We call this an open interval. Good?
Mm-hmm.
Yeah.
Close bracket is the same as this, but we actually include the a. So x less than or greater than or equal to a, but still less than b. Close bracket on that side means we include the b. Close bracket on both sides means we include the a and the b. This is called a closed interval. Open interval, closed interval. Good?
Mm-hmm.
That, it means just the point A. This means all the numbers greater than or equal to A. This means all the numbers greater than A. This means all the numbers less than or equal to B. This means all the numbers less than B. This means all the numbers. Any questions? Open interval, closed interval, special intervals. Open and closed.
Are you saying that those are only if A is greater than?
But that's a policy topic.
Are you saying that only if B is greater than A?
Yeah, so anytime you see this interval notation, it is an assumption that the right hand thing is greater than the left hand thing.
What if it's not?
So
Then you're using the notation wrong. Anytime you see this notation, it is assumed that B is greater than A, with exactly how we define the symbol. You do not have the interval 5 to 2. That doesn't make sense. Our definition of intervals only works with A less than B.
So it's ordered.
Mm-hmm.
It is ordered. The order still matters inside these things.
It's not an ordered pair.
But it's not an ordered pair, as in that's not a two-element list. This is an infinite set. It represents an infinite set of numbers. Good? Okay, so that's interval notation. And then we'll try and get through the last of our proofs. So going back to proofs using positivity. All right. Proof if A is positive, A inverse is positive. Right? So let's go over it. 1, notice that if A is positive, so maybe I should put a then in here to help with how we see this. If A is positive, comma, then A inverse is positive. So once again, it's an if-then statement. Everything I'm proving, it can be broken into if-then statements. I'm going to assume this and use that to prove this, right?
Mm-hmm.
So A is positive means that A is not 0, right?
Mm-hmm.
Because each number is either positive, or its additive inverse is positive, or it's 0. But it can't be positive and 0. So I'm guaranteed that if A is positive, then this symbol is defined to begin with. Alright?
Mm-hmm.
So, since A is not equal to 0, A times A inverse is equal to 1. Right?
Mm-hmm.
Then either A inverse is positive and negative A inverse, or negative A inverse is positive. I wrote my typo in my notes. That's why I'm confused. Now, the reason I took the time to say this is that tells me that A inverse is not 0. Remember, if I have a number times a number, and it doesn't equal 0,
Then you have.
if either of those numbers are 0, this product would have been 0. Right? So the reason I'm stating this is so I know that A inverse is either positive or negative A inverse is positive, but either way, A inverse can't be 0. That's what I was trying to capture here.
Yeah.
Good with that? Okay. So, by way of contradiction, I'm going to assume that this is a positive one and get a contradiction. So then this has to be the positive one.
Okay.
You with me? Assume negative A inverse is positive. For, let's see, then if we take that thing and we multiply it by A, negative A inverse times A is equal to negative A inverse times A is equal to negative 1 is equal to negative 1 is positive. Make sure we understand that. So I'm assuming that this thing is positive, right? Now I already know that A is positive, right? Actually, I don't even need that information, sorry. So I take that thing, I multiply it by A, and I get that negative 1 is positive.
Which is a contradiction.
Let me make sure that, here's what I'm trying to say. I know that A is positive, right?
Yes.
And I assume that negative A inverse is positive, right? So here I have a positive times a positive, right? Which has to be a positive.
Right.
So this has to be positive, which means this has to be positive, which means this has to be positive, which means this has to be positive. Contradiction. Why is that contradiction? Why is it negative 1 positive?
Because there's no negative
Less than 0.
It's less than 0, but that's a bad way to say it because we don't really know that's less than 0 yet. Why is negative 1, why is the additive inverse of 1 not positive?
Because it is.
Zero.
Because 1 is greater than 0.
We show that 1 is positive. For each real number, one and only one thing happens. Either the number is positive, or its additive inverse is positive, or the number is 0. Is 1 0?
No.
No, so rule out that case. So either 1 is positive, or negative 1 is positive. Only one of those two things can be positive.
But 1
1 is positive. So negative 1 can't be positive.
Right.
That's our contradiction. Does that make sense? See the logic there?
Therefore.
5. Therefore, A inverse was a positive 1. Good?
Yeah.
Alright. Next one. That marker. Prove. If A is greater than C and B is greater than C, then, oh, and C is greater than 0, sorry. If A is greater than B and C is greater than 0, then AC is greater than, oh jeez, I did the other way, but that's right underneath, so I was looking wrong. Then AC is greater than BC. That's what we're going to prove. If I know that A is greater than B, I can multiply both sides of that inequality by a positive number, and the inequality is still true. Very common operation that we want to do. Good?
Yeah.
And right now, we already know that something being greater than 0 and something being positive is the same thing, right?
Yeah.
Okay. So let's continue. So, remember, we have an if-then, so we're going to assume that we have A, B, and C where this is true, and show that leads to this being true. So, since A is greater than B, the exact definition of that is, then A minus B is positive or is greater than 0. Oh, that's not what I'm doing. Then A minus B is positive. Sorry, I'm doing this different than I thought. 2, since C is greater than 0, then C minus 0, which is equal to C, is positive. With me?
Yeah.
Then I can take the product of those two things and it's positive. Then A minus B times C, which is equal to AC minus BC, is positive. Follow my logic there?
Yeah.
And then that's the definition of AC is greater than BC.
Yep. That was actually cool.
Therefore, AC is greater than BC. It's the definition. Good?
Yeah.
And now we'll do something similar, except for we're going to swap the Z. We're going to say, why talk it instead of just show it? We'll try to squish it in here.
You just square.
Alright. Prove if A is greater than B, and this time we're going to say 0 is greater than C, or C is less than 0. I don't know which one of those is better to read. C is less than 0 instead of C is greater than 0. Then you flip the inequality. AC is less than BC. Right? Sorry. Trying to. Does that read okay?
Yeah.
Okay. So, since C is less than 0, what does that mean?
C is negative.
0 minus C is positive. 0 minus C, which is equal to negative C, is positive. And so, a positive times a positive is positive. I'm going to use the fact that, I'm going to use the same logic we used here to save on space. Since A is greater than B, we already know A minus B is positive, right? Here I showed that negative C is positive. So a positive times a positive is positive. With me? So I'm going to use that same information. Since A is greater than B, A minus B is positive. So A minus B, which is positive, times negative C is positive. Good? Now do the other one. Then A minus B times negative C is equal to negative C times A plus negative C times negative B is equal to negative, I'll write AC instead of CA, negative AC plus CB is equal to CB minus AC. So walk you through all the algebra real quick. So I know the product of these two numbers is positive, right?
Mm-hmm.
Which gets us here. Now I'm going to do the algebra. Start with the distribution. I kind of skipped a step. A minus b is the same thing as a plus negative b, right? Now distribute, which gets us this. Negative c times a plus negative c times negative b. Negative ca, we know we can pull out the negative and we can rearrange the terms, right? And then two negatives multiply together gets rid of the negative signs, right? And then I can do that in any order I want. I can write that as cb plus negative ac or cb minus ac. Plus and negative and minus are the same thing. That's the definition of minus, right? So that's positive. Therefore, CB is greater than AC. That's our definition of what it means for CB to be greater than AC. See it?
Yeah.
Wonderful. That's it. That's the preliminaries.
Sequences. I hate sequences. How are you going to do
There you go. You might have struggled with sequences when you came across them in your calculus class. You don't hate sequences. Now you know. Sequences are great. Alright, so your exercises, your test for next week, your take-home test that you can work on together if you'd like, I don't care, is the exercises for Appendix A. They're on whatever page I said they're on in your syllabus. You can start working on those right now if you'd like. I forgot to tell you guys last week, I will stay after school every day that I teach to help you get started on your assignments. I strongly, strongly recommend that at the end of each class, you look over the problems that you're going to have to do over the next week, try and figure out which ones you think are going to challenge you the most, and talk to me about them.
Okay, I'll be here every night. You are here.
Does that make sense?
Mm-hmm.
So I will be here. I typically stay till students are ready to go, but what did I say till last year? Like 6:30ish?
Anyway, as long as to 7:30. Some nights.
Yeah, so I stay as long as I feel like I need to, but typically I'm here till about 6 or 6:30ish.
That's when people.
What
usually
is
have
the
to go.
appendix?
What is it? It's at the end of the book.
Oh, the appendix.
I gave you the page in syllabus. It's like 560 something.
Okay, I'm going to pull out my syllabus.
So we can start that. Maybe actually what we should do the rest of the time is introduce an inductive set because proof by induction gets students stuck like crazy. Do you remember proof by induction?
You prove for one case and then another case.
So let me just kind of ask a question to lead to it. This is a side note. You don't need to worry about this for your upcoming homework. You probably won't even see why this is relevant yet until we come to maybe just like introducing it to you now outside the context of proving will make it not so scary for you. So let's say I've got the secret set. And I want you to figure out how all the elements in the set that you can. So I've got some secret set A.
Oh, counting?
No. I've got some secret set A, and there's numbers in there. And I want you to figure out all the numbers that you can figure out are in there. And I'm only going to give you two pieces of information.
Oh, these.
I'm going to tell you that 1 is in A. Okay? The other piece of information I'm going to tell you is that if some number k is in A, then k plus 1 is also in A.
Oh, I got these.
I don't know these.
So that's the two pieces of information I'm going to give you. What's everything that you can tell me is in A?
What?
So you know that 1's in A.
We don't know if K's an A.
You know that if you can find some number in A, then that number plus 1 is also in A.
So you found that
So
one
we
is
know.
an A.
So then what's in A?
Then 1 plus 1 is an A.
Which is?
2.
Perfect. So now you know that 2 is in A. What else is in A?
3.
Look, it says if you find a number in A, and 1 is in A.
If some number is in A, then that number plus 1 is in A.
Okay.
Good?
Yeah.
So I told you 1's in A. Now you know that 2 is in A. And you also know that
3,
and
4,
and
5,
etc.
and infinity.
so you now know an infinite number of elements in there. Notice if I would have told you, let's play again. I tell you 1 is in A and that 1/2 is in A. Now what you know is in A. In order.
1/2. 1.
1 and
1 and
1/2.
1/2. 2.
5.
5 over 2. 3. 7 over 2.
Wonderful. You get the name of the game?
Yep.
Okay. So when we do a proof by induction, we try to prove that a statement is true for all the natural numbers. So you notice if I did this, and that just gives you the natural numbers.
Yeah.
That gave you 1, 2, 3, 4, 5, 6, 7, 8, all the natural numbers. So here's the way that proof by induction works, and we'll go over it again next week. It's just good to get it a couple times. You're going to prove that a statement is true for all natural numbers, first you prove that the statement for the number 1 is true. And then you prove that if the statement is true for a number k, that implies, if the statement is true for some number k, that implies that the statement is true for some number k plus 1. So if you show that this is true and this is true, then you show that it's true for all natural numbers.
So what have we been using proof by what for these? I know we do by way of contradiction.
That's called direct proof and proof by contradiction. We didn't go over the contrapositive. First time I come across that, I'll show you contrapositive. But let's do a proof by induction real quick just to give you a feel for it. Okay? Because it's kind of weird the first couple times you see it, but then you get used to it. So on the common one, let's prove that. Have you guys seen this?
Mm-hmm. Summation.
The sum of all the numbers starting at 1 and going to n of all our numbers is equal to n times n plus 1 over 2. What do I mean? I mean, for example, 1 plus 2 plus 3 plus ... plus 1,000 is equal to 1,000 times 1,001 over 2. Add up all the natural numbers to some number n, doesn't matter what n is, then the result will be the sum. That's what we're going to prove. Ready? So, first we want to show that the statement holds for 1.
What's 1? In this one.
1 would be
That, so, we call that the base case. So, base case, we handle 1. We say, let n equal 1, then the sum of all the numbers from k equals 1 to 1 of k is equal to 1 is equal to 1 times 2 over 2.
Oh,
Which is
we
equal to
actually
1.
use that example every time we play, proving by way of induction.
This is the pretty standard first proof you did for proof by induction.
Oh!
So I'm going to prove that this is
I
always
see
true.
Okay, I see where I was mistaken. Okay, now
We're proving that this is true for all natural numbers n.
Right.
So first we prove it's 1.
And
Then we show if it's true for k, it's also true for k plus 1.
Right. Okay.
Right?
Mm-hmm.
So if we were thinking about what is the set of all numbers that this is true for, we're going to show it's true for 1, and then we're going to show if it's true for k, it's also true for k plus 1. So the set of all numbers that this is true for is the natural numbers. Just like this gives you the natural numbers. You with me? So now let's continue it. So remember to do if this, then this. You assume this and use it to prove this. Right?
Yeah.
So then we do assume for n equal to j. I can't use k because I use k down here. Let me change my notation here to match up there. So we'll switch this out with a j, switch this out with a j, and then I'll use k here, switch this out with a j. So then, assume for n equal to k, that the sum of all the numbers from j equals 1 up to k of j is equal to k times k plus 1 over 2. You with me?
Mm-hmm.
We're just going to assume that, and we're going to use that If this is true, then this is true. That's a then. So now I need to show that this is true if this is true. So then the sum all the way up to k plus 1, showing j equals 1, of j is equal to k times k plus 1 over 2 plus k plus 1. So we added k plus 1 to both sides of this equation. Good? That's what I did here. If I take this and I add k plus 1, I added one more term. So now we're going from 1 all the way to k plus 1 instead of just 1 to k. And then on the right hand side, instead of just that term, I also have k plus 1. Right? And because I'm tired of being on my knees, I'm going to rewrite this up here and then show what it's equal to. So get rid of this. So k times k plus 1 over 2 plus 2 times k plus 1. Good. Multiply this by 2 and divide it by 2, so I can put them all under the same denominator. Factor out my k plus 1.
This is how arrow did all its proofs. I've actually had such a hard time doing it.
There.
Oh.
And then the sum from j equals 1 to k plus 1 of j is equal to k plus 1 times k plus 2 all over 2. Exactly what we were trying to show.
Yep.
We were trying to show if it's true for k, then it's true for k plus 1. This is exactly what you get when you plug k plus 1 into this formula. So we showed this formula is true for 1. Then we showed if this formula is true for k, if this is true, then this is also true. It's also true for k plus 1. Okay? That's proof by induction. We'll go over it again next week because it's what kids struggle with this all the time, but it's such a useful proof technique. It's used all the time, especially we're going to be using it because we're going to be talking about sums a lot. Okay, so we'll conclude with that. You guys are free to go, or if you have questions on your homework, I'm happy to answer. Otherwise, I'm going to start filling up the board for my discrete math notes. Turn off the camera.